let's have a look at the assembler, which I built with the aid of ChatGPT. Now, I'm no programming guru, and Python is not the language that I'm used to using, so I'm used to writing stuff in C, or I can produce stuff in Excel VBA, and it does just kind of what I need it to do for the projects that I create. But I wanted to get something more professional together for the CPU, and I wanted a better assembler, and so I decided to jump into the land of Python. Now, this is my first bit of code, although I have written tiny snippets of code before a few years ago in Python, but not very much, so I don't really know the language. But I do know, having programmed in other languages, the general constructs that I can use. So the program here is actually goes down to about 1500 lines, but there's the spaces in between, so there's maybe about 1000 lines of code. Now, I'm not going to talk through every single line of code, that would just be a bit, well, really boring, but I'll try and talk my way through the general structure, so it gives you an idea of the structure of an assembler if you decide to go and build one for yourself. So we'll start off at the top here. Now, I've got 3 dictionaries here. So the first dictionary contains the opcodes. So these are all of our instructions. So you can see here I've got the data instruction, the load, the store, jump, jump to subroutine, push, pop, add, and you can see the rest of them all the way down. And you can see there's on average about 4 for each of them, because each of them has 4 different addressing modes. Now, the addressing modes I started off with generating the exact same addressing mode for each command, but then I realised that that was just a bit silly, because I was limiting myself, because some commands don't really need some addressing modes, and it's much better to have some commands with other addressing modes. So I kind of, as I built up some code, I had a look to see the stuff that I was missing, and I simplified some of the addressing modes for some of the commands. So along with the example, and you can see there's actual examples here, along with the examples of the addressing modes, the examples of the instructions, I've also got in here the 8-bit opcode for the instruction. So you can see it's mostly an 8-bit opcode, but there are some instructions which, for example, the jump instruction, which I've actually got a 12-bit code here. And there's other instructions down here at the very end where I actually use the full 16 bits. Now, the reason for that is that some of the instructions are going to use both registers, register A and register B. So I'm going to have 8 bits for the opcode, and then I'm going to have to source the other 4 bits for one register and source the 4 bits for the other register from somewhere else. And in some of them, we have the 8-bit opcode, and we have an 8-bit opcode, and we have 4 bits which are fixed, and we only go to get 4 bits from one of the other registers. And then some of the simple commands at the bottom, for example, the clear flag command, we don't need to get access to any of the registers, so it's just a full 16-bit code there for it. So that's the first part there, and it covers quite a lot of instructions. I don't know how many there exactly. I think there's about 120 or so, round about that. Now, the second register here we have is the register. The second dictionary we have is the register dictionary. So this covers the registers that I mentioned up here, which we have to go and get the last 8 bits of the full instruction. So register R0, if for example, is all zeros, and then it goes to 1, 2, 3, and we run all the way up through. And remember, I've designed the CPU so we can really, each register can talk to each register. So we've actually got 15, I think, here, as opposed to 16. I think there's actually 16. So we've got 16 options here. You can see we've got the floating point register, the index register, the stack pointer, and there's a temp register, control, instruction address register, and so on and so forth. So we've got access to all of these registers from all the other registers. Now, finally, because I'm dealing with an input into the assembler, which will take characters, I need an ASCII table as well. So we've got the ASCII table here. Now, the useful thing here is that whenever I use ChatGPT, I could just simply ask it, can generate the ASCII table for me. It generated the ASCII table. Of course, it wasn't quite in the right format, but then all I needed to do was say to it, literally say to it, I had it loaded up, and I had the voice recognition on, and I asked it to place double quotes at the beginning and the end of the ASCII code, and also append at the beginning the hash value. Okay, now I append the hash value because all literal numbers within my assembler start with a hash. So I was able to ask ChatGPT just simply to go ahead and generate these. So now the main body of the code really kind of starts here. So as I was using ChatGPT, I found that the most efficient way of using it obviously is you have to know what it is you want. We still work under the ethos of garbage in, garbage out. So if I ask it to do very small limited things, then what happens is it goes and generates the code, and I can then take that little snippet of code, have a little read through it, see how it works, try it out. If it works, that's fine. I move on and ask it to generate something else. So this sort of thing here is the kind of thing that I would have asked it to do. So I went in and I had a file format in mind, and I would say, I need you to go and find a text file that exists in a particular path. Okay, and it's in the same path as the file, the assembler file here, and ignore any other files. So it would go in and it would find the text file. So I just made sure there was only one text file in that folder, and it would go and it would open up that text file. So it would just get and generate this code here for me, and of course it would come in and generate any of the error checking as well. Now another thing I did as well is I took the original file, which is my assembly language file, and I made a little copy of it because at some point further down in the code that was going to be getting, a part of it was going to get written over, and at the very end what I do is I just copy out the original file back over on top. Okay, so it's just the way I kind of generated it. But again, I got ChatGPT, I basically asked it to provide me with the code which would allow me to do that, and this is the code here. But of course I don't just take the code and just copy and paste. I read over the code and I see the nomenclature and I see how it works, and I think, okay, that's good, at least I can follow it if ever I have to go back in and redo any of it myself. So that's the first little part. Now the next little part here, I'll try and break it down into some sort of logical order. What I'll do is I'll go down first of all and we'll look at the second pass, because the second pass is easier for me to describe. So I'll get into the second pass section here. Okay. So it's really starting round about here. Okay, so the second pass is at this point. Now, what we want to be able to do is, in this second pass, we're going to have a file, and this file is going to, it's not going to have any labels on it or any kind of declarations. All of that will have been stripped out, okay, and all of the jumps would have been worked out. So you've got to jump from one part of the code to another. So all of that would already be in here, okay, and it'll be generated from what's above here, which we'll talk about just after I've gone over this. But what we want to do here is we really just want to find the opcode which has been written down in a text file, and we just want to make a comparison and say, well, we want to find that opcode, and we want to find the opcode in the opcode dictionary. So we need a method really of just finding the actual zeros and ones here relative to each of these. So the most obvious way of doing it is the first part of the opcode here is in capital letters. So I keep all of my opcodes in capital letters. None of them are in lowercase letters. So I could ask for it to go and look for, say for example, the word store. So straight away it will run through the dictionary to find store. Now it means that we've got then a very quick way of finding the store command, but having found the store command, there's going to be 4 possible values for it. Okay, so then I could work through and then have a single test for finding the store, and then I'm going to have 4 tests to find which one is of the store commands it's in, and I can do the same for the rest of those. Now, I didn't quite do it like that. What I actually did was, and I think it was maybe, when I look at it now, is probably a bit more complicated, but made the code a little bit shorter, is that I had a look and I broke all of these down into their sizes. So for example, the data command has got 1, 2, 3, so it's got 3 entries, and you'll find that the other commands here, there's some commands here that have got 4 entries. For example, there's the add command, add #5 RARB, so that's got 4 entries, and there's other bits of code that have got 2 entries. For example, not 700, it's got, if you can see that down here, not 700 has got 2 entries, and there's single entries. So I worked through it in terms of 4 entries, 3 entries, 2 entries, and 1 entry. And also I worked through it in terms of the actual name for the code. So that's how I was able to match what was written in the text file with what is written in the dictionary, and then return the value here for our opcode. And that's what's happening down here within this section. So this would be the group of 4 here, and there would be a test here really for the assembly language file, which is just a text file. So I would take the text file and I would split each line into the groups of either a group of 1, 2, 3, or 4. And if this was in a group of 4, I would begin and it would compare the first part of that group of 4 with the first part of the group of 4 in the dictionary, and it will then have found not the actual opcode, but it would be one of 4 of them, and then after that I would have to work out which one it was, and that's what each of the options here covers. Okay, so it works out which one it is. Now, once you've worked out which opcode that you actually have, then you've got to return the value for the registers, register A and register B. Okay, so within each of these if statements, I'm going to have to return the actual value that is within the register. Okay, so that's what each of these lines here does. So I did that for the 4, the 3, and then the 2 is here, and then for the value of 1. Okay, so that's the 1. Remember the 1 part's here. That's the 1 part here. Let's see, so the group of 1 here. So there's very few here for the group of 1 because it's only covering 3 or 4 different commands. And I just kept a note of what each of them is covering. So that's really about half of the code. There's probably, when I look at it now, there's other better ways of doing it, but this, which I worked out afterwards, but at least this works and I can maintain it, and it does go in and it picks out all of the right values which I require. Now, the other stuff at the top is a bit more difficult to talk through, because what I have to do is I have to create a program counter, and the program counter has to know the length of each of the opcodes. So for example, what I mean by the length of each opcode, I don't mean this length here. This, for example, the data command is 1, 2, 3, so it's got 3 parts to it. It's not that length I'm talking about, it's the actual length of the whenever it gets stored in memory. So for example, this data #5RB is an immediate mode, so the #5 gets stored in memory. So it means that the data RB part is going to take up 16 bits, okay, or if you call it 1 byte, if you just say 16 as a byte, okay, and then the next address is going to be the #5, so it's going to take up 2 consecutive 16 bits, or if you like 2 bytes, not 8 bits, 16-bit bytes, okay, so it's going to take up 2 of those. And other commands here, there's actually a move command, and there's another data command. This data command here, it actually takes up 3 memory locations. So there's the data, which is 16, I'll just keep calling it a byte, it's 1 byte, and then the #5 is the next byte, and the next one after that, 500, is the next byte, so it's taking up 3. So we can have instructions that will take up 3, 2, or 1 bytes, and we need to be able to count along each command as it comes in, and as we decode it, we need to know how many bytes each of them take, and most of what you've got down here is in order to generate that. Okay, so once we've generated that, what we have to do is we have to be able to use labels. So we have to have a label. Now all the labels are in lowercase letters, okay, and numbers. So you can't have a label with an uppercase, okay, so that's how I'm able to distinguish them. And of course, whenever I create the course, I'll explain this in the course, and I'll show how the assembler works, okay. How we actually generate the language in the file, okay. So this part here, again, it works with the labels, and it has to generate the particular label positions and replace the labels with the actual address dependent on the program counter, which depends on the size of each of the individual instructions that are written in the file. And that's really what most of this part here does. Now there's a few other things that it'll do, and that is that we have to be able to write our values in 3 different ways. We can write our values in as a literal form. Okay, so the literal form would be, well, there's 2 ways we could write it in a literal form. So the hash 5 would be the number 5. Now, if it doesn't have a hash in front of it and it's just a 5, then it means a memory location. And that's the most fundamental part of the way I've done this here. It's split into literal and memory. And you always have to know when you're dealing with a memory location and when you're dealing with a non-memory location, because the non-memory location is always going to have the hash in front of it. Now, secondly, as well as those 2 options, we have to be able to put them in 3 different ways. So it has to recognize it as either an integer, in which case it would just be, say, for example, hash 5. Or if it was a binary, it would be a binary number. It would be hash 0b and then the binary number 101010. Or it could be a hexadecimal, in which case it would be a hash and it would be 0 cross and then the number, the hex number. And the same thing would happen for the non-literal, so the actual memory addresses. So in memory addresses, it would just be, say, for example, the number 5, which is integer, the 0b101, which is the number 5 in hex, or the 0 cross 5, which would be the number 5 in binary, or the 0 cross 5, which would be the number 5 in hexadecimal. So in all instances, what I do is I take all of these different, the 3 different methods of putting the number in, so the integer, binary, or hex, and I convert them to an integer value. So through the whole code, it always deals with an integer value, but at the very end, it outputs it in a copy in binary and a copy in hex. So that's what some of these sections here do. Now there's another thing as well, is that I've created a few assembler declarations. So for example, we have the 3 main declarations are the EQU, that is equals. So that's setting up a value. Now it doesn't actually save the value to memory. The value is just set within the assembler. Okay, so you're really creating a label with a value associated with it. Now the other one is called the DC, which is defined constant. So again, it's going to be used in order to define a value, but this time the value is saved into memory. And finally, we're going to have the DS, which is defined storage. Okay, so it's going to again define a value, right? But it's going to define a set of memory locations, but we're not going to put anything in the memory location. Okay, those will be populated whenever you run the code. So those are the 3 directives that I wanted to build in, but I also wanted to build them in so that I could put in, for example, text values. So I can write in, for example, DC1 is going to be in single quotes, hello world, and it will read in hello world and it will convert it to the ASCII value and save it in the memory locations, okay, one after the other. So that's what all this section here is for. That's the DC and that's the EQU there. And again, they had to do it separately for the jump because the jump acts slightly differently. It's going to have a change in program flow. Okay, so this section here deals with the change in the program flow, but also have complications. For example, you might have generated a loop, but the loop will actually come. The number for the loop will come from an EQU directive, and that EQU directive will in effect the value in it will be just a word. Okay, so then you have to replace that word with the actual memory location. Okay, and then we have to do the jump. Okay, and the whole program here has to be able to jump as well in order to keep track of all of the positions. So a wee bit of confusion there, a bit of programming in order to get that done. Now that's pretty much it here. We've also got a start address and also an origin. So the origin defines where the actual program starts, and the start address defines where the data is going to start. Okay, so I don't want to talk through any more because I could go on for probably hours. And then we take the final the output from this pass1, as I mentioned, and it's actually a file called pass1, and then we open it up. And then whenever we open it up, I'll show you just now if I have a little look. I'll find the files here. So if I into Python, and for example a pass1, I don't know what's in it at the moment. Oh, there you go, there's an example. So that's pass1. So you can see here in this instance that there's no words in this. Okay, everything has been, say there's no words other than the actual opcode word, but everything else, all the other jumps and all the labels, it's all been replaced via the actual address. And you can see this is the address actually in an integer value. Okay, so that's what the pass1 would come out like, and then we would have to take this, and then the second pass would generate the machine code. So that's pretty much the assembler, and that's the kind of the anatomy of an assembler. And we get the final output at the bottom here, which really just outputs it in a value of a binary value and also a hex value. And at the bottom here, it just does a few extra bits of housework. So that's the actual assembler. Okay, so now if I was to actually create an assembly language program, so this would be a program, say for example a program here. Okay, we'll call it test.db. Okay, so that's me testing out all of the different directives. So we have an origin 0x8000. Okay, so that's in hex. I could actually write 0 and a large cross as well. So if you mix these up, so I've tried to make it as user friendly as I can. So I've offered different methods of writing things in. So that's the start address of the actual program, and here's like a compare this thing here. It says fifth with the contents of R0, and there's add fifth into with the contents of R0 and save the value in R0. And the start address here is going to be 0x8020. So that's the start address for our declarations. Okay, so, or if you like, it's going to be where all the variables and all of the data are going to be held. So that's 0x8020. So it's 20 positions. So it's actually in hex. So it's, what's that, 32 memory locations further down, and we start all of the data and all of the other variables and constants. That's where they're saved. So for example, we could do ds1, so define storage. We'll call the storage fourth, and it's 10. Okay, so it's actually going to be, in this case here, it's 10. That's 10 decimal, so it's going to be 10 memory locations. And you can see here it's not hash 10. Okay, it's not hash 10. Hash 10 is a literal number. If we're talking about memory locations, we always talk about the value 10, okay, when we refer to a memory location. So that's 10. I'll set aside 10 memory locations, and the first memory location will be have a label on it, which will be fourth. Now the other one here is define a constant. Now the first define constant 1 is called first, and the constant is actually hello. And the second one here is called second, and it's world. So what's going to happen is, by this define constant, what it's going to do is it's going to take this value h, change it into ASCII, and it's going to stick it in a memory location, the very next available memory location, and this will put the E, the L, and the O in the next memory location. Okay, so in effect what it does is it creates the data command, which just loads these up. So you're preloading all of this up before we start the actual assembly language program. And we've got the DC3, which is third, and that's got a colon. We've got this other one here, which is EQU. So you can EQU, and it's the fifth, and it's got M. Okay, so you could put M, or you could put any number in it as well. It's up to yourself. You know, that I've just been testing this out with the actual characters. So it means that if I was to, I'll just save it here. If I was to run through the actual assembly language with this file, so I just come in here and I can say it's been run. Okay, so that's it, generated it, the assembly language. Now, difficult to show you here because it's the way I've generated this, but you can see here that we're going to start off with, what I'll do is I'll show you the first pass. So that's pass 1. So that's pass 1 here, so you can kind of work out from this what is happening. So let me just get rid of this one here. Right, and I'll bring up the actual code, which is this one. So that's the code we started off with, and this is the first pass. I'll move over a bit. There we go. So you can see it. So you can see here it says origin 0x8000. Now, and the first part here, it says this part here is 0x8020. So this is in hex, and it's really telling us that this DS1 says set aside 10 memory locations, okay, and we'll call it fourth. So it takes the first 10 memory locations. Now the first 10 memory locations from, this is 8020. Now 8020 in hex, you'll find is going to be 32810. Okay, so that's in an integer value, sorry. So this is the first memory location here, and it takes the value h, which is 104 in ASCII, and it puts it into this memory location, and it takes the next value e, puts it in this memory location, and it works its way all the way down, and it just preloads these. Okay, so it just generates these individual codes to preload them. And then we've got the other two here at the bottom, actually at the bottom here, which are, well, that does 10 of those here. Okay, so you're going to have the other one here, which is the EQU fifth M. So again, that's this one here. Okay, so it works its way down through all of these, and you can see, so that's what memory location 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You don't see this one here because this one here would not preload anything. It's just part of the assembly language, and it's worked through, and it disappears once we've actually ran the bit of assembly language. Okay, and we've got the compare, and the compare here, you can see the fifth is, if you come down here, it's the fifth, which is M. So it's comparing the M. Now the M is going to be 109. Okay, so it's comparing 109 with the contents of R0 and putting the result in R0, and it's adding fifth. So it's adding 109 to the contents of R0 and putting it in R0. So I can do a whole load of stuff with this. Now another thing that we can do, obviously, that we never showed here, and it's a big part of it, you can put in a loop. So you can put loop 1, and it's a colon, and it can generate, it'll generate whatever it wants to do, and you could go along here and you could put in JMP loop 1, and then it'll jump to the beginning of loop 1. Okay, so it'll take care of all of that. And also we've got jump to subroutine, so it will do those jumps and it will update the stack, and it allows us to jump into subroutines, and from those subroutines to other subroutines, and it allows us to jump our way back to the beginning again. So it does pretty much everything that a kind of you would want an assembler to do. It's quite powerful, and it's really going to help us out whenever we start doing some designs, okay, some coding. Now that's been a long video. I know it's a long video, and of course not everyone would have got to the end here. Not everyone's interested in this kind of detail. But that's all for this video. The whole code and everything will be available to you within the course. And if you ever want to talk over the code or how I've generated it, then feel free to get in touch. Thank you for listening. I'll get you on the next video. Goodbye.